Hello everyone, and welcome back. Today we're going to start looking at a very important kind of motion, which brings us to section 14, oscillations. Oscillations are, as I said, a very important kind of motion because they are extremely common. While it might seem that what we're looking at is a very specific kind of thing, it will actually demonstrate a type of motion that occurs in all sorts of different systems, not only just mechanical systems, but electrical systems, continuous systems, as we'll see next lecture, all sorts of different places. Let's imagine that we have a spring, okay, and I'm going to put a mass on the end of this spring. Okay, there we go. I hope you can see all of this. Now let's imagine that we displace this mass and then release it. What's it going to do? Well, you can maybe imagine what's going to happen, but let's give it a try. So I'll move it down, release it. It starts oscillating. This is what we would call an oscillation, some kind of repetitive motion that goes and repeats itself over and over again. Okay, let's take a look at that, but rather than doing this vertically, I'm going to imagine, or let's imagine that we put the spring horizontally. And let me draw that down, and then we'll take a look at some aspects of that. So here I've drawn the mass on the spring, and we've arranged it horizontally. That's so we don't have to worry about the gravitational force, which would be one more force acting on the mass. We'll only consider the force from the spring. And likewise, we're going to assume that it's riding on a frictionless surface again, so we don't have to worry about an additional force. All we need to do is think about the force that the spring is exerting. Let's imagine that there is some length of the spring that the spring will take when there is no force acting on it, what we would call the rest length or the equilibrium length. So we'll assume that the position of our mass when it's at equilibrium, in other words, no force acting on it, we'll set that as our x equals 0 position. And it doesn't matter if you want to measure the front of the mass, back of the mass, middle of the mass, it doesn't matter, whatever. We'll just call that point and always measure the position of the mass from that point. The position then of the point on the mass when there is no force acting on it, we'll call that x equals 0. And positive values we'll assume to the right, negative values of x we'll assume to the left. So let's imagine what happens when we pull on the spring, when we move this, so this end we'll assume is fixed to some immovable wall. So the left end of the spring is not going to move. What happens when we move the end of the spring to the right? What happens? Well, the spring pulls back to the left. So if we give the mass some position, a positive x, then the force will pull back to the left this way. In other words, the force is going to be in the negative direction. If we compress the spring, now this is a little bit hard with some springs. It needs a little openness, so to speak, in the spring. But just imagine if we compress the spring pushes back that way. So if we give the mass a negative position, then the force is in the positive direction. So the force always seems to be in the opposite direction to the displacement of the mass. Positive x, negative force, negative x, positive force. While it is not necessarily true, we will assume that the applied force, or the spring force, is going to be proportional to x. So if we pull a little bit, we get a little force. We pull more, we get more force. Pull more, or move the end more, we get more force. Likewise, compress it a little force, compress it more force. What we'll do is we'll make the assumption that the force is directly proportional to x. This is assuming what we would call an ideal spring. Now, obviously, this will not work forever, so to speak, for any value of x. If I pull or if I move the spring too far, I'm going to distort the spring. I'm going to pull it beyond its elastic limit. I'm going to, excuse me, bend the coils, and it will never come back to the way it was. Likewise, I can only compress it until all the springs are right up next to each other, and then I can't really compress it anymore. So this only is going to work for a reasonable value or a range of values of x within what we would call the elastic limit of our spring. So it's an approximation. But when we can assume that, we have what we will call an ideal spring. So what can we say about that? Well, we know, how can we make this an equality? Well, we know that the force is going to be in the opposite direction to x, positive, negative, negative, positive, and we'll put in a constant of proportionality that we will call k. And k is referred to as the spring constant. And k basically tells us how strong the spring is. If we stretch it a little bit, if we get a big force, that means k must be a large number. So a very, very tight spring that's hard to pull apart. If we can pull it a lot and only get a little force, then k must be very, very small. So if we have a spring where we can pull it a whole lot and not get much force, that's a weak spring, and that would be k is small. So k basically tells us the strength of the spring. Large value of k, a strong spring. Small value of k, a weak spring. And then we've got this relationship, F equals minus kx. And this is what we call Hooke's law. This is named after Robert Hooke, who was a contemporary of Isaac Newton. So what kind of motion can we get, or will we get, when an object is experiencing Hooke's law? Now let's keep in mind, and I want to be very careful about this, the force that we're talking about here is the force exerted by the spring. So if I stretch the spring to the right, the force I am applying with my hand is to the right, but the force the spring is applying is back to the left, your left. So we need to keep in mind that this force that we're talking about is not the force that we apply to stretch the spring or move it one way or another. It's the force that the spring is exerting. So let's just be careful about that. All right, very, very good. So what kind of motion do we expect? Well, what we expect is, although I can't really do this sideways, but we will get a very similar motion to this if we do it vertically. So we're getting some motion up and down that's repetitive. Let's take a look what mathematical solution we might get for something like that. What we have is F equals minus kx, Hooke's law, and we know the force from Newton's second law must be equal to the mass times acceleration, the acceleration of the object, the mass m. And the acceleration we know is the second derivative of position with respect to time. So this must be m d squared x dt squared. If we divide by m, we have d squared x dt squared equals negative k over m times x. This description here, a differential equation. This is a second order linear regular differential equation, or ordinary differential equation, as opposed to a partial differential equation. This differential equation represents what we will call a motion that we will describe as, or that we'll call simple harmonic motion. This is an extremely, as I said, extremely general result. We see this very, very often. Sometimes just SHM for short, but let's keep this in mind. Whenever the acceleration of the object is proportional to the negative position, we will end up with simple harmonic motion. In other words, whenever the force is proportional to the negative of the position. What is the solution to this equation? Well, we know we're going to get a position as a function of time, so x as a function of time. What is the solution for that? Well, there are different ways of solving this. You can use polynomial expansion and put it in and differentiate and then equate similar terms, different ways of solving differential equations. But what I'm just going to do is I'm just going to give you the answer. And actually, for one of the homework problems, I'd like you to verify that this actually does solve this equation. The position as a function of time, a solution we can write as A, and I'll go back over all of the parts of this in just a second, cosine omega t plus delta, where omega is the square root of k over m. So this quantity here, k over m, that's the square root of that is omega, or omega squared is equal to k over m. So actually another way that we could write this equation is d squared x dt squared equals minus, this would be omega squared x, or we could bring it to the other side and say plus omega squared x equals 0. So that's another form of writing this equation. And just keep in mind, anytime you see this equation, you'll know you're going to get a solution that is simple harmonic motion. Okay, so let's take a look at this solution. What kind of qualities of this result can we find?